Well, hello and welcome YouTube to Mr. Robinson's Q&A Power Hour. It's been a minute. I think it's been a minute, maybe a month or so since I've done one of these here, but I think it's naturally just worked for my students and what we've been able to do and, what we need to learn here now. 6 questions worth in Mr. Robinson's Q&A Power Hour today on rational expressions or equations or functions. I'm guessing, and I'll take a look right now or as we do it, but I'm guessing most of the questions will be on graphing the rational functions. I think my students have a pretty good handle on the things from before because they already knew what a factor, they understand the idea of multiplication, common denominators, things like that with fractions. But we'll see. Maybe questions on extraneous solutions and stuff as well. But only 6 questions. But that does mean I could probably get deep into them if they're asking questions on graphing rational functions. Maybe I'll try and throw in some examples for them. So maybe it'll be a full hour, maybe 10 minutes per question. I have no idea. You do because this is already recorded and you can see the time slider. All the questions are in the description section down below there with timestamps on them as well. So enjoy this and we'll see how it goes. So let's go and take a look at, where is my little sheet for this thing here? I think it's this one right here. Yes. All right, let's go ahead and look at what these questions are right now. And the first question is, how to find out whether an equation has a horizontal asymptote versus a slant asymptote. So this is a graphing rational function question right here. The answer is really simple. As far as when you compare degrees of these things. But let me first get a breakdown of, I got to write this here somewhere. Sorry, I haven't done this in over a month, so I forget where all my little tools are. All right, here we go. So first things first, when we're talking about graphing rational functions, a rational function is something that has x in the denominator, where that x likely can't cancel out of the denominator in any sort of way. Doesn't mean x's can't be in the numerator as well, though. So let's say that you have some sort of f of x thing right here. Now, the main note that I write to my students is, like, if you have some polynomial up on top of a rational function like this, ax to the m plus blah, 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 over bx to the n plus blah, 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 blah. Basically, 2 polynomials where you have x's potentially in your terms here, because this could be m to the 0 power, and m to the 0 power is 1, and it could just be a constant on top, right? But you have some polynomial on top divided by some polynomial on bottom. X is raised to the m and n powers here. M may be equal to n, but it also may not. And my big note here was, if m is greater than n, you're going to feature technically an oblique asymptote, because I want to get a little further into what else it could be. I'm just going to go ahead and call it a slant asymptote for now. However, if you've been in, so here, I'll say slant or oblique. If you've been in any of my videos before, I believe I did call them oblique asymptotes at the time, and I probably should. I should stick to that. But the idea is that we're always going to be choosing m values that are just 1 degree larger than n. If it was 2 degrees larger, again, something I can get deep into potentially, then it would actually be something that's not necessarily slanted, but it's not horizontal either, called an oblique asymptote, because it can become a quadratic asymptote or a cubic. And I actually want to do one of those with you guys here. This is why this will probably take 10 minutes now that I think about it. If m is less than n, and I'll kind of get into the why in these in just a moment. If m is less than n, you'll have a horizontal asymptote, but not only that, it will be at y equals 0, which is on the x-axis. I'll get into that in just a moment. And then if m is equal to n, you also have a horizontal asymptote here, but it's going to be at y equals a over b. The leading coefficients right here, those actual values, you would actually divide those. So now, their question is how to find out whether it has one versus the other. Well, it's horizontal if these are the same or if this is bigger. That answers your question right there. If they're not the same and this is bigger right there, then you'll have a slant or an oblique. So that answers the question. And if that's all you wanted to know, then then you can move forward on the thing. For me to get a little bit deeper into it, though, I'm going to try and keep these on the screen as well as I can while I make an equation, or I make one up. Let's go to, it really doesn't matter. Let's do f of x equals, wait here, I'm just going to put x's on top and bottom. So if I have an x squared over x squared, now look, x squared divided by x squared is 1, right? Here, let me throw in some other things, otherwise you'll just say, I wasn't listening, what's happening? There we go, okay. So right here, the leading terms dominate. As long as we can understand and agree that leading term dominance is the most important aspect of any polynomial, then that'll also be true for rational functions. It doesn't matter what's here as long as there will be some sort of remainder to provide asymptotes. The idea of asymptotes is approaching values that we never actually touch or cross in end behavior format. And what we're talking about here is when we plug in really large values of x and when we plug in really small values of x. So when we look at an equation like this right here, we will actually feature a horizontal asymptote that will be at y equals 1, because 1 times a billion squared divided by 1 times a billion squared is 1, right? If this was a 2x squared right here, 2 times a billion squared divided by 1 times a billion squared is 2, right? The top is twice as large. Yeah, there are some little things along the way right here that keep the asymptote, that keep the points above or below the asymptote a little bit as you get to large numbers, but the leading terms dominate there. So horizontal asymptote here because these are a tie. However, if this guy's larger and this is x cubed like this thing right here, suddenly the cubic dominates. You know what a billion squared is? Some number with 18 zeros. You know what a billion cubed is? Some number with 27 zeros. No, wait, hold on. I don't know if I got that right. I think so. Some number with 27 zeros. You know how much money you have with 18 zeros? More than anyone. You know what I mean? 27 zeros versus 18 zeros. It's a massive difference. And that's just for a billion. What about a gazillion, right? So now suddenly this one dominates right here. And what happens when you divide something relatively small by something relatively massive? You approach 0. And that's why this one shows up right there. Now what if the top was like this, a cubic? Now you're dividing something massive on top divided by something relatively smaller on bottom. And then that thing is getting larger, just larger toward infinity or negative infinity, depending on what your numbers are. Maybe toward negative infinity that way, and then it approaches in that direction. So this is where you start to feature slant asymptotes, but more importantly, because you're doing x cubed divided by x squared. X cubed divided by x squared is x to the first power. And x, again, you plug in a billion for x, that becomes a billion. You plug in negative a billion for x, becomes negative a billion. Y is now affected by the values of x that you plug in. I mean, in that it's dependent on x. Whatever x is, it's actually growing or shrinking based on that. So there's that concept there. Now, the concept we never ran into, the oblique asymptote, is what if you had x to the fourth power? X to the fourth divided by x squared. Well, that's x squared. So now y is affected by x in a quadratic form. You know, now a billion squared is 18 billion, and 18 zeros and things like that. So you can have oblique asymptotes such as these. Not that we're going to do them. But you have oblique asymptotes such as these, and we could. It would be fun. I'll do one with you because I have no better use of my time. So that's the general idea there. It's all about the comparison of degrees. And that's because when you do long division on this, you end up with a quotient and a remainder, and the quotient ends up representing your asymptote, whether it's a slant, whether it's an oblique, whether it's a horizontal, and something like that. So that's the basic answer to the question, and I answered it right here to start with, and I'm exploring it a little more, and I'd like to do that. What I did pre-build just in case, and it looks like I'm going to be using it here, is I need to make my own examples, but is where is it? This guy here is a graphing calculator thing where I can draw graphs for you, sketch them, and kind of see what comes out from them. So let's start with something where there is some sort of, let's just do 1 over x minus 1. 1 over x minus 1, and let's look at that graph. So this graph right here, and I don't have any asymptote drawn. Hold on, I can set this up. Y equals mx plus b. Perfect, y equals 0. Okay, so if you look at this graph right here, and hopefully you see the blue dotted line. Let's see if I'm still on camera. I'm sorry, this is a little rough for today. Okay, there's that one. Let me get the vertical asymptote. X equals a. Let's call a 1. Okay, we're not talking about vertical asymptotes. That's just dividing by 0, whatever. But this one, 1 over x minus 1. This is 1 is a constant. That means degree 0. This is x to the first power. That means degree 1. So it's going to have a horizontal asymptote on the y-axis, or on the x-axis, on y equals 0. That's because you get 1 over, and again, when I say massively large, I mean like a billion. Plug in a billion for x. What's 1 over a billion minus 1? What's 1 over a billion? It's like 0, right? So what happens is as x gets super huge right here, these values might as well just become 0 right here. If I zoom out enough on this thing, it just looks like a cross right here. But if I zoom out enough, this thing will eventually just tell you 0. It's not really 0. It's that this computer kind of gave up on telling you what it could be. It only uses 3 decimal places and it rounds to that. It's something above 0, not exactly. I could actually use I could say f of a billion. Let's do that. F of 1 billion. So check out these. Oh, you can't see them. Let me drag this up. F of 1 billion. I don't know how many zeros that is. But notice here, see those numbers? I don't know if you know scientific notation right there, but it's not 0. It's not 0. It's not 0, it's not 0, it's not 0. But it's super small. It's like Avogadro's number. Super small. Eventually this computer will give up and say, yeah, that's 0. It's not really. Well, maybe it won't. Maybe it'll just keep doing this. Look at how this computer still works with me. It's still not 0 in its eyes. So that's actually quite interesting right there. Anyway, all those zeros, still not 0, even though it's 1 divided by that number, like a Google -1, or a Googleplex even. If I copied and pasted a bunch of zeros, maybe eventually I can hit that 0. Oh, see, now it says, yeah, you know what? I can't give you any more numbers. It's probably 0. It probably ended up at 256. No, it didn't. I don't know. Anyway, I'm talking too much. So there's that one. 1 over x minus 1. True power hour format for me to just talk. You find the other question if you want to find out more. If you want to listen, it's pretty fun. Now listen, if it's x squared minus 1, different graph, right? I can't account for what kinds of graphs I'll actually get. This would be x -1 right there. So there's that graph like that, right? Okay, quadratic, because x plus 1, x minus 1 is in the denominator. Still y equals 0 horizontal asymptote, because the denominator is still bigger and so much more bigger. A billion squared is much more than a billion. It's going to flatten out towards 0 a lot faster than the other one. Okay, that's great. So we have those x minus 1 bits like that. Now let's go ahead and put in let's do a -2x plus 1. Sure. Now this one is now suddenly going to have, and I wanted some character with this to give it. Let's do y equals -2, -2. And then I can get rid of these, and that's good. Okay, so this one right here, there's a tie, x to the first and x to the first power, right there. This one now is a horizontal asymptote at y equals -2, you can tell. And for what reason? Because, again, plugging in a billion, you get -2 billion divided by 1 billion. And look, the +1 -1 do matter to give the graph the character that it gives it, right? Otherwise, the answer would just be -2. If there was nothing else here, it would literally just be a flat line like that on the asymptote, but there wouldn't be an asymptote anymore. The idea of the asymptote is points that we stay above or below for true end behavior. And the +1 -1 give us a remainder to keep us just above or below the asymptote in that way, but it is at -2, because as x gets really large, the y values start to approach -2. If I did long division on that, I'm going to go ahead and write that in, so give me one moment. Let me clear out something on this thing right here. All right, let's go back to... let's go back to this. All right, if I do f of x equals, and I'm going to do long division on a couple of these. This is going to be a true power hour, just power through all this. -2x plus 1 over x minus 1. Let's do long division on this. -2, or synthetic, but I'm just going to go ahead and call it long. X goes into -2x -2 times, and then you get -2x plus 2, and subtract that result, and you get -3. So this thing becomes, as division, -2, with a remainder of -3 over x minus 1. So the quotient, this -2, ends up being the horizontal asymptote, or the asymptote, horizontal, slant, oblique, whatever it is. The quotient becomes that, and this becomes the remainder. How much above or below -2 your points end up becoming. See, if I plug in a billion for x, the y value is -2. Oh, -3 over a billion, or 999,990,000, right? -3 over a billion. That's really close to 0. We're subtracting something really close to 0, but that means that number is just not -2. It's just below it. Just below it. That's why on this graph over here, when we go back to this, our points are just below -2 as we go toward a billion, as we go really far out. And that's what's happening there with the remainder and the quotient. And that's why long division is a nice way of going about doing some of this stuff here. Okay, let's do another one. Let's go ahead and add a quadratic with it. Let's call it 3x squared. Yeah, why not? 3x squared. Let's do a 3. Suddenly, we're going to have something different. Now look at the graph first. Let's hide the asymptote. Look at the graph right there and see what's going on. The vertical still x equals 1, okay. But suddenly the points don't approach a finite value. Now they go on forever toward positive and negative infinity. It looks very linear in a way because they are approaching a linear slanted asymptote. And that's because suddenly we have x squared divided by x, or specifically 3x squared divided by x. This is approaching some sort of linear asymptote. And what is it? We're going to have to actually kind of find that later. I think I saw a question when I was looking at it. I think there was a question that says, how do you sketch a slant asymptote on a graph? You know what? I'll still answer it here. sketching the slant is doing long division, and I'll probably go back to that and kind of repeat that again, so I'll keep the slide up. So as far as that goes, give me one moment. I'm going to do long division on this guy. Maybe all the questions, I don't know what all the questions were. I did see that one. Maybe I'm going to answer all the questions in this one thing, and then boom, power hour over. So let's do long division on this one now. And let's do 3x squared minus 2x plus 1 over x minus 1. Okay, you're going to check this out with me here. So you can tell none of this is ever preordained. Okay, or prearranged. So let's do long division on that one there. 3x squared minus 2x plus 1 over x minus 1. X goes into 3x squared 3x times, and multiply those. You get 3x squared minus x. Subtract those results, and you get negative x plus 1. And x goes into negative x negative 1 times, and that's negative x plus 1. And so, oh, I don't want a zero remainder. Hold on a second. Did I do that right? Oh, minus 3x. I'm sorry. Let me do that again. Plus x right here. Plus x plus 1 plus x minus 1. Yeah, I should get a remainder, right? Because they don't divide equally there. And that should give me 2. So I don't know if I did that right. Sometimes I question myself at my own long division practice. Actually, I never do that, so I don't know how that happened. But anyway, so that becomes 3x plus 1 plus 2 over x minus 1. So here's that function, right? The quotient, once again, 3x plus 1. The quotient represents your asymptote. This is no longer horizontal, though. Now it has a slant to it. 3x plus 1. Y equals, right? Think about this. Your slant asymptote is y equals 3x plus 1. You graph that line. You graph that line. Those are the points that the y values get close to. But because of this remainder, it stays just above or below that point at any x value. So if I graph y equals 3x plus 1, I'm going to do this on this other one over here. If I graph y equals, let's call 1 and 3x plus 1, and show that, there is our slant asymptote right there. And you can tell that that's what it's approaching. So how do you graph that is another question I think was asked later, so I'll go to the graph later as far as how do you do slope-intercept form. I'll go and do that with you. But you can see that we get really close and really close to that thing, but we're never quite on it because we're just above it. Right here, you're plugging in some values, 2 over a billion. You're adding, or 1 over a billion, it doesn't matter. You're adding something just above or subtracting something to keep it just below. Right there. Now, the one that I'm really curious to do, and I want to do it right now, is I want to show you an oblique asymptote. And the reason that it shows up is because of adding something that is another degree larger. So let's just create an x cubed. X cubed plus 3x squared, da, da, da. All right, take a look at this graph, first of all. Oh my goodness, this is crazy, right? What is even happening right now? I'm having trouble kind of fathoming some of this stuff here. But what you're looking at right now is to the left of the asymptote, it does this, and then whoop, like that. And then over here, it comes from the top and does that. Where's the asymptote? What's it approaching? Well, let's come up with it. And I just got to write x cubed on this one and then do this division one more time with you guys. For those who are curious and watching, I hope you have fun with this. Now, the question, how do you graph it? You got to know how to graph a quadratic. And I'm not going to do that. I'm just going to create the equation that they give us. We're not in for it right there. All right, so I put an x cubed right there. Let's go ahead and erase this. Let's do one more. This last one I'll do. See, this is now called an oblique asymptote, or a quadratic asymptote, or whatever you want to call it this time. And I really should be doing, you know what, let's do synthetic division this time, just because I have this many terms. So 1 is my root, and maybe you want to still remember how synthetic division looks. And you got those. So we're going to have 1, 4. Now, you might wonder why I didn't do synthetic division before. Because a lot of times you would end up dividing by something that's not linear, not a linear root right there. Sometimes it's a quadratic and things. So you just probably want to feel comfortable in your shoes on the other one as well. So this is now f of x equals x squared plus 4x plus 2 with a remainder of 3 over x minus 1. So this is now your asymptote. It's no longer, it's not horizontal. It's not even slant. It is oblique. So oblique, I guess to you will just mean non-horizontal. Something that is skewed. I don't know. something like that. So the oblique asymptote this time is y equals x squared plus 4x plus 2. That is the graph. Those are the y values that it says just above or below in some instances on this graph. So I'm going to do y equals x squared plus 4x plus 2. Y equals, let's take a look over here. Sorry. And then I'm done with the question. I'm really sorry about spending so long on this thing here. Y equals x squared plus 4x plus 2. All right, take a look at this right here. Let me thin this one out a little bit. There we go. Okay, take a look at this right here. Check this out. This is interesting. Remember, it's all about end behavior right here. See this asymptote right here, this parabola? This is what the curve approaches to the left. Yeah, maybe not right there. It doesn't have to approach right there. It's underneath at those y values, but because the y values are very small, you can separate a little bit. And then it gets closer and closer to it up there, right? Obliquely. And then over on this side, notice the oblique asymptote curving up here. There are no, it's again separating itself, and there are no points at x equals 1. And then you see them approaching again on this side, obliquely right there. So when I zoom out, and I can give this one a little bit more width to give a little more character right here. And then, like I said, I should probably retire this kind of question. Maybe I answered all the other questions along the way. Here's kind of a better look at those things with a different scale right there. You can see that parabola take form. See that parabola take form as this curve approaches the asymptote right there. Really interesting. But anyway, so again, conclusion. In conclusion, how to find whether an equation has a horizontal versus slant asymptote. You're comparing the degrees. If you're in standard form in your thing, you're comparing the degrees of your numerator leading degree and denominator leading degree of your polynomial, the degree of the polynomials. And as far as division goes, if they're equal, you have a horizontal. If the denominator is greater, you have a horizontal, but at y equals 0. And then you can do long division on any of the other ones to figure out what the exact thing is. And if the numerator is greater in degree, then you have some sort of oblique. It's a slant asymptote if it's 1 degree larger. It's a quadratic asymptote if it's 2 degrees larger. It's a cubic if it's 3 degrees larger, like that, and use long division to figure out exactly where they are. All right. How do we find the x and y intercepts? Okay, this is something else where I feel like I could go really long on. Just to answer, because the question is potentially asked in such a way that I'm not saying you don't know what x and y intercepts are, but if you really, really, really do know what they are, like the whole gist of them, then it's a question that you'll know how to answer on your own as well. So let me go here. Let me erase some of this stuff right here. And let's just make sure that let's revisit what x and y intercepts are in general. Let me I can pull a graph into here. Okay. I have some graph right here. It's not rational. It's more of a polynomial, right? And we've done these. Here's an x-intercept, here's an x-intercept, here's an x-intercept, here's an x-intercept. Anytime you cross the x-axis, you have an x-intercept right there. Now, what are these points? And I don't know if I hit points perfectly, but this is around -7, 0. This is -2, 0. Let's pretend like that is 4, 0. Let's pretend like that is 9, 0. Okay, those are points where they cross the x-axis. Those are known as x-intercepts. What do they all have in common, number-wise? They are all values of x when y equals 0. X-intercepts are values of x when y equals 0. Now, this is important in an equation because when it comes to finding x-intercepts, what you have to do is set y equal to 0 or f of x equal to 0. Whatever equation you have, what was the last one we saw? X cubed plus 3x squared minus 2. Oh, I have it right here. Minus 2x plus 1 divided by x minus 1 equals f of x, right? There's that equation. What if I turn this f of x into 0? You ask yourself, and this is a different equation, right? But you try and find out what values of x give you 0. Now, you don't want to divide by 0, but you want to divide from 0. So you want to set the numerator value equal to 0. You want to set this equal to 0 right there. When does this equal 0? And then you solve for x. Obviously, I'd have to use rational root theorem and things like that to factor, and then possibly use quadratic formula because these are probably not really good x values. You'd have to check on that graph that we had, where those x values were, and those x values on the previous thing that I did. Here's an x-intercept right here. It's probably irrational. It looks like that's the only one. So the others are imaginary, I'm sure. I didn't plan for anything like that. So, so there's that, right? So x-intercepts are values of x when y equals 0. But more specifically, in a rational equation, what you'd want to do is you'd want to set the numerator equal to 0 because you want to find out when the numerator equals 0. right? Not the denominator. The denominator dividing by 0, you either have a whole or a vertical asymptote. But when the numerator equals 0, you get to divide 0 by something, which you get 0, which means you'd want to factor the top. And we would probably factor first anyway. This is obviously a way different question. It was made up. But that's what x-intercepts are. They are values of x and y equals 0. Set 0 for y, solve for x, and you probably solve by factoring, so you can use zero product property. If this times this times this times this equals 0, then either this equals 0, and then you solve that way. Now a y-intercept is the value of y when x equals 0. So right here, this is a y-intercept, in this case 0, -3. Now in a function, you can only have a single y-intercept, right? In a function, you can only hit the y-axis once because it has to keep going left and right, and you can't repeat y values. But even if you did, let's say I had a circle like this, and you have a y value right there, y value right there, they are technically both y-intercepts, and there would be 2 of them. But anyway, what do all the y values have in common? This is 0, -3, pretend like this is 0, 4, 0, 9. They're all values of y when x equals 0. So y-intercept is a value of y when x equals 0. And in an equation, this is pretty easy to do. You substitute 0 for x. You go back to that example that we had, x cubed plus 3x squared minus 2x plus 1 divided by x minus 1 right there. Okay, there's f of x equals, well, what does f of 0 equal? You substitute 0 for x. You get 0 cubed plus 3 times 0 squared minus 2 times 0 plus 1 divided by 0 minus 1. You get f of 0 as 1 over -1, which is -1. That's where it crosses the x-axis. When you substitute 0 for x, you cross the y-axis. I don't know if I said x-axis. You cross the y-axis at -1. So if we go back to this right here, did it hit 0, -1? You betcha, right? That was the equation that we were kind of looking at and using. That's where it crosses, right? So, and if you notice what I did strategically here, although I didn't have the factored form because I was calling attention to it for the x-axis, the x-intercept, I said for the x-intercept, you might want to factor that thing. Use zero product property because you're setting this equal to 0 and you're solving. The y-intercept, however, I probably want to use my standard form because when I substitute 0 into a term with x in it, the term will go away. So I'm just left with looking at my constants in the numerator and denominator right there. Now, it's possible to not have any x-intercepts, of course, because if they don't factor, or if you have imaginary solutions, you notice that this cubic only had one x-intercept because the other two are, I guess, are imaginary. Okay, whatever. And it was an irrational x-intercept, but okay. So we had that one. But also, what do I want to say to that? But also the y-intercept, there might not be a y-intercept because if you plug in 0 for x, you might end up dividing by 0. So if x is a common factor in the denominator, you might be dividing by 0, which leads you either to a vertical asymptote on x equals 0 on the y-axis, or a whole if you're dividing 0 by 0. But you would have already found that before you found the y-intercepts because you probably already factored and you probably already noted where the wholes potentially were and the vertical asymptotes as restrictions. Okay, so hopefully that answers your question there, and I will keep moving forward. 2 questions in, half hour. You can see power hour taking full effect. Okay, I didn't really see any of these other questions yet, so let's keep going into what's the best way to determine where the lines go on a graph when not many points are given. When not many points are given, I'm guessing they're saying, or when not, yeah. Now, when the lines, what's the best way to determine where the lines go on a graph? You mean where you draw the curves, right? I assume we're not talking about asymptotes anymore, but when not many points are given. So this question really hits toward what I was doing with my students. Let's go back. I don't know if I'm going to make up an example, but let's draw something that kind of works in the mindset. What we had before, what I did with my students before was we unfortunately had a horizontal asymptote on the x-axis, which can potentially, not always, because my students have seen it cross horizontal asymptotes in middle behavior, it can potentially mean no x-intercepts. See, if it's off the x-axis, it's got to hit the x-axis somewhere unless there's a hole, but you'll also find it. It's got to hit the x-axis somewhere because we got to approach an asymptote, right? But if it's on the x-axis, they don't always cross the x-axis. They don't always cross asymptotes, so there's something like that. And you have a vertical asymptote, say that's even on the y-axis, which means definitely no y-intercept. You plug in 0 for y, you're going to divide by 0, so nothing there. And then maybe there's even another asymptote along the way, another vertical, something like that. So let's say you have this, but it never crossed the horizontal because sometimes it doesn't. and then it never crossed the vertical either. And because the horizontal is on y equals 0, that means that the numerator is larger than the denominator, so you can't do long division on this to figure out anything else from it either. Your quotient in it is 0. It can't go in, x squared can't go into x cubed can't go into x squared any number of times. So if you have an x squared over x cubed, unfortunately, you're left with not getting any points that cross there unless there are certain x-intercepts, and let's pretend like they're not. So this question is, I have no holes, so I can't get locations of hole values. It doesn't cross the x-axis at all, and it can't cross the y-axis without there. How do I get points on this graph? Well, us graphing this, and I know you guys see this more as process than anything else, but let me just kind of hit this little nugget to start. Us graphing these things in different ways can all be resolved by using a table. No matter what graph you do, you can always plug in an x, get a y, plug in an x, get a y, do it a bunch of times until you can see the pattern and connect the dots. There are faster ways to do that given certain means, so we try and come up with what they are. We've talked about transforming using a, h, and k in certain situations, and we'll be doing it the rest of the year based on a certain kind of function. We even did it with rational functions, but they were the basic rational functions where a, h, and k were present. Now we're looking at some where they're not present, such as the one you just saw, right? And even in polynomial things, we had a specific way we're factoring, finding those points, right? We just have to get the general behavior of the graph. And that's all I'm asking for you to do here, general behavior of the graph. Well, the general behavior of the graph is first dictated by asymptotes, because where we approach lines. So let me go back to that. Where we approach our these lines here, these asymptotes, really gets us the idea of, are we graphing above? If so, we're graphing above, then it hits that. Are we graphing below? If so, then it looks like that. Maybe this one even graphs below, right? There's a chance it can do that. So, maybe the graph does something like this. I don't know. I didn't make up an equation right now. I'm just making this up. But we know that based on asymptotes, we can get some critical features of this graph, not have to worry about points and not worry where it jumps and does whatever like that. So we're saving ourselves by finding asymptotes through factoring and finding out where we divide by 0. Okay. So there's that. The next aspect is there are easy points for us to generally find. Okay, now I know I'm going the long answer of this, but there are easy points for us to generally find. X and y intercepts are generally easier to find. Y intercepts because you just plug in 0 for x. What happens is terms go away. You don't have to compute anything. You just saw that. You plug in 0 into 3x squared, you get 0. You plug in 0 into negative 2x, you get 0, right? So those just turn into 0. You're just left with dividing the constants. So it's an easy point to find. Plug in 0, terms go away. The x-intercepts, you plug in 0 for y, and those are also easy points to find because if you're already factored, zero product property is a very special thing, right? When things multiply to become 0, one of them has to be 0. That's not true for any other number. You multiply numbers to become 10, one of those numbers doesn't have to be 10. Right? And as long as one's 10, so 0 is very special in that way. That's why finding x and y intercepts are so nice for us. Plus, it determines where the sign needs to stay below the entire time that we're through those points. It's going to stay negative the entire time from one x-intercept to the next and things like that. Or it's going to stay above the entire time. So those are critical points. They're good to have. A hole is necessary for us to have on a graph. It's another feature like an asymptote. There's no defined value there. If I have a hole right here, I have to jump that point. So despite the fact that it may be some weird fractional value. It is a required thing to say that we don't hit that value. So holes are something that we're going to get anyway, so we might as well get a location. So I forget where I'm getting at with the answer because the question is, how do you graph without those things? What I'm telling you is why we don't use a table. Because we can generally find, let me lift it above for now, we can generally find other features of this graph that are like, okay, here's the y-intercept, here's an x-intercept, there's no x-intercept right here, and here's an x-intercept right there. And I find out I don't cross the asymptote at all. Maybe we say, or we find out we cross the asymptote. We find out it crosses the asymptote right here, and then we have some graph that has to therefore approach here because nature of approaching asymptotes, it doesn't hit the x-intercept right here, and it doesn't cross, so we know it's going to be above. And then this one stays below because we know it hits the x-axis right there and, does all that. So based on that, we can get the general behavior of the graph with it, which is awesome. That gets us everything we need to know. But what if, and I know it's a long-winded answer, I hope this is helping you a lot. What if we don't ever cross the x-axis just because the asymptote's on there, we approach it but we never cross, and we can't have a y-intercept right there, and there was no hole that we found. What do we do? This is where we can refer to a table. You can listen, you got to plug in points. You got to plug in points. I plug in the idea of points, though, because my understanding with the asymptote is if I get a negative value for y right here by plugging in an x that's less than 0, if I plug in a negative value and I get this point right here, that means it is below. And if I plug in a value between 0 and 5 and I get a positive, then it is above. And if I plug in another one that's also positive over here, then it is above, right? So at that point, I gotta plug in something, right? We were plugging in points before. X-intercepts are points, Y-intercepts are points. Holes are not points, but they are locations that the curve crosses through. So we found areas where the curve crosses through, and that's what we use to get our thing. And that's what we're gonna do here. That's where I tend to use what's called a sign chart. What I'm doing is I'm skirting away from computing actual values. I'm not computing actual values. Instead, all I'm doing is I'm coming up with the general gist of what the graph is doing. Let's see what this equation would look like in factored form right here. This would be, so we'd have to divide by an x and an x minus 5 because those are our vertical asymptotes. We can't have a hole, and this has to be larger on bottom than it has to on top. So this could be, for all we know, this could be 2x plus 1, like that. Okay. No, we can't have an x-intercept, so let me give it a constant. I'm sorry, let's just give it a 1. Okay, this could very well be the graph. I could even plot this on Desmos, and you'll see that it should be this graph. So 1 over x times x minus 5. No x-intercept because there's no value of x where we get 0. And check that out. When I said 2x minus 1, it would have crossed. This would have had a horizontal at y equals 0, but it would have crossed the asymptote at x equals 1/2, and it would have had something like right there, and it probably would have done something like that, and blah, 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 blah. Kind of neat, but we'd still have to find some other points. Anyway, so let's do 1 over that. It didn't hit anything else. Okay, so here's what I would do right now. You can plug in values for x, and I would plug in a single value for x in this region right here, where x is less than 0, because I would know that since it doesn't cross asymptotes or intercepts, I would know the sign stays the same the entire time. If it's underneath, if it's negative, I graph underneath. If it's positive, I graph above. And then I would plug in a point between 0 and 5. Same thing. It either has to stay completely below or completely above because we never cross the axis. And if it's positive, I graph above. If it's negative, I graph below. And then to the right of 5, I have to plug in a value. And then what's going to happen is it's going to stay either positive or stay negative. It can't cross. And it won't cross based on the nature of the factoring. Now, again, I'd like to use factored form. Instead of using x squared minus 5x down here, I'd love to use factored form because, listen, let's plug in a value that's left of 0. Let's try negative 4. Now I have to do negative 4 squared. I have to think about what these numbers are. I have to compute this and I have to see how the signs change. Minus 5 times negative 4. That might not sound like a lot to you, but I'm not trying to get what the actual value is. I'm trying to get the sign. As far as the sign goes, I would get negative 4, which is a negative number. Negative 4 minus 5, which is a negative number. Right? They're negatives, and 1, which is a positive number. And I don't care what the value is. I care what the sign is. So here I would get a positive divided by a negative times a negative, or a positive divided by a positive, which is positive, which means to the left of x equals 0 here, I would get a positive number. It would be a negative 4, I have a positive, whatever, so it approaches from the top, like that. And that's what this is the idea of a sign chart. I don't have to draw the chart itself. I don't draw a chart itself, I just have to plug in a number, see what the value is. Same thing right here, in between. I have to figure out whether it's positive or negative. So let's try 2, plug in 2. Positive over positive times negative. 2 is positive, 2 minus 5 is negative. That gives me a negative result, which means I'm now down below. And then plug in something greater than 5, like 10, that's positive over positive times positive, which is positive. So this one's now above, like that. Okay. So that's the ultimate one where it's you don't have any points, and you got to plug some things in. But you already found asymptotes. You already found out what it doesn't have. Doesn't have x-intercepts, doesn't cross the horizontal, anything like that. So it lets you know all the other information. Just say, what is the sign of a value in between? All the other ones will have that value. Draw the general nature of the curve as a result of that. And I sketched that really fast. Let me graph that one for you really fast as well. Let's hide asymptotes here and go to true power hour here today, guys. What was it? 1 over... I'll just call it x squared minus 5x, just to show you it should still be the same thing. Minus 5x. There it is. Okay. I forgot the scale is kind of weird. How do I zoom square? All right. Okay, so it's the same idea of the graph, right? We have vertical asymptotes at 0 and 5, horizontal asymptote at 0, and then it stays above and below the entire time right there. Maybe my curve isn't perfect with it, but I don't need to get what the specific values are. That's not my goal. It's not what the specific values are. It's where it stays above, below, to the left and right of does it cross anything. And I did that. They stayed above and below that way. Now, they don't always just do that, because your question was what? Sorry. I'm still rummaging through this. Your question was, what's the best way to determine where the lines go when not many points are given? So that was one with no points. But, I just did talk about one as well, where say you did find a point, and I want to hit that home as well. So let's say that instead of saying 1 over, it said 2x minus 1 over, where we still have all of this. The features are still the same right there. So 2x minus 1 over x times x minus 5. Suddenly, though, this now has an x-intercept. Suddenly it has an x-intercept wherever this equals 0, at x equals 1/2. That means it actually crosses, and this isn't going to be a pretty graph based on that, but it's going to cross, or at least touch the x-axis right there. That makes another critical point, though, because what can happen here? Let me do a different number. Let's do 2x minus 4. Let's make it that's a little hard to see. So 2x minus 4 equals 0. Add 4 divided by 2 would be x equals 2. Let's do that. X equals 2. Okay. That means it crosses the x-axis right here. Okay? That's another critical point, though, because what happens at x-intercepts? The sign changes from negative to positive, from positive to negative, or it could keep its sign. The graph might do this. The graph might do this. Might do this, but the graph also might do this. I don't know. And the graph also might do this as well. So we don't know which one it's going to do. This is where sign charts still matter, not just to the left of 0, to the right of 5, and in between, but also now between 0 and 2, and between 2 and 5. This is where at some point I probably would just draw a sign chart just for myself to give myself a visual version of what we're talking about here. Here's x equals 0, here's x equals 2, here's x equals 5. These are the only places where it either crosses the x-axis or doesn't have an x value, and then the signs can potentially change. As we truly see that graphs can do that, and then that right after. They can change sign from positive to negative right at the change of between to the left and right of 0. And again, we would plug in values, and I would honestly factor 2x minus 4 into 2 times x minus 2, right? So now when you're plugging in numbers, you know that 2 is positive right there. So anyway, you plug in some values. I plug in a negative. Again, negative 5. That's a positive times negative, which is negative, divided by negative times negative, which is positive. Negative divided by positive is negative. Suddenly this graph doesn't go up above. Suddenly this graph is down below like that. This is a negative value to the left of 0. In between 0 and 2, let's plug in 1. 2 times negative 1. 2 times positive times negative divided by positive times negative. That's a negative over negative, which is positive. That actually means it comes from the top right here. It comes from the top and curves itself down. I don't care what the value was. I care what the sign was. When I plug in 3, positive times positive over positive times negative, that's negative. It will go down below, and it will do that right there. And then let's plug in 20. Positive times positive over positive times positive is positive. So this one's positive here, and so it starts from the top and it finishes up there. So suddenly, having that x-intercept and crossing the asymptote right there changed the nature of this graph a lot, at least on the left side of it right there. And of course, it crosses the asymptote. So let me go ahead and graph that one, and then I'll be done with the question. I'll mention one more thing, but I'm not going to do any more problems. So 2x plus 4 over that. Did I type that right? 2x minus 4. Excuse me. 2x minus 4. That is not a minus. There we go. So there is that graph right there that I was referring to, right? It has that to the left, it's underneath, in between, and it crosses at x equals 2 right there. So you got to plug in points. You can use a sign chart physically or mentally. You can plug in points. You're going to use a table. How do you find points on a graph? You plug in values for x. But again, we need features on it. X-intercepts are easy to find. You just saw me find one. They help understand the behavior of the rest of it. So you try and find intercepts where you can, try and find holes where you have to, if they exist, and then get any other points for sign chart and behavior. The last thing I wanted to mention, and sorry if you keep hearing a whistling, my phone is telling me I have a notification. The last thing that I want to mention is if your asymptote is above or below the x-axis. I don't want to use a sign chart on the original function anymore. Now everything's probably shifted up in some sort of way. I don't care what the equation is anymore, but now everything is shifted up, possibly in some sort of way. You're asking if you're above or below the asymptote now. And the asymptote is all about your quotient and its remainder. And the question is the remainder positive or negative on some horizontal, right? Y equals 2 plus some remainder, or y equals 2 minus some remainder. Are we above or below 2, not 0? It's not are my y values positive or negative, is the remainder positive or negative now? So when you use a sign chart, use it on the remainder, in which case try and factor that out if you can. Okay, that's a lot there, and I'm 45 minutes in after those questions here. All right, next question here. How do you sketch a slant asymptote on a graph? How do you sketch a slant asymptote on a graph? So I kind of answered that in question number 1. It was in a big way. I hope that you can kind of find part of my answer there when I talk about using long division. But the answer is, if a slant asymptote exists, that means that the numerator is larger than the denominator for degree, and you have to use long division to come up with the quotient equation. The example that I used before, and I don't think I drew it, I think I used Desmos for it. So the equation that I did before, I still have it written somewhere from a previous thing. I think it was 3x squared, and I don't. I think it was 3x squared minus 2x plus 1. F of x equals 3x squared minus 2x plus 1, I think, divided by x minus 1. I think we kept that at x equals 1 right there. Okay, this one features a slant asymptote because the numerator is 1 degree larger than the denominator. So how do you sketch it? Just like from before, and I did it before, use division. You don't have to do long division if this is linear factor. So I'll go and use synthetic again like I did last time. That will be faster for me. But you use division on the thing. So 3, 3, 1, 1, and 2. And what you get is a rewrite of your equation into 3x plus 1 and then plus 2 over x minus 1. Okay, hold on, I have an alarm thing going off. Give me 1 second here. Okay, anyway, so this guy represents the slant asymptote. It is the quotient of your thing. And I mentioned y in the first one. It's all about what points are just above or just below that line. So the line is y equals 3x plus 1. So as far as how do you come up with the slant asymptote equation, you got to use division. Long or synthetic based on what you're allowed to do for the thing. Use division, and you would have a slant asymptote if the numerator is 1 degree larger than the denominator. How do you sketch it? That's y equals mx plus b. Y equals mx plus b. That is slope-intercept form. You use the y-intercept of 1, and you could plug in points, but you use the 1 y-intercept, and then you use the slope 3, or 3 over 1. So I'll go ahead and draw that one for you. I'm going to cover all this up right here. Y equals 3x plus 1. You start at 1, y-intercept, and then you rise 3, run 1, rise 3, run 1, like that. It is 3 being the slope is 3 divided by 1. That's what makes it that. And fall 3, run 1 to the left. And this becomes your slant. You know, the horizontal asymptote of y equals 3 would just be a horizontal line, boom, like that. Or y equals 1, because that is the slope of 0, right? Y equals 1 is y equals 0x plus 1. It has a slope of 0. This one has a slope of 3, and then it crosses like that. So that ends up being it. If I did an undo on my graphs enough here, then I can come up with that equation again. Let's see if I can find it. Give me 1 sec. I'm undoing, undo the did. Okay, I have it again. Did enough undo. So if I go back to here, this is the equation y equals 3x plus 1 right here. It crosses at 0, 1, and then it rises 3, runs 1, and it has 1, 4, rises 3, runs 1, and it hits 2, 7 right there, right? That is drawing the graph right there. In slope-intercept form, you know that your fraction, your slope can be a fraction quite often. So if it was y equals 1/3 x plus 1, and y equals 1/3 x plus 1, then you would rise 1, run 3, and plot those points right there. But you just draw it slant. And if it's negative 1/3 x plus 1, you would fall 1, run 3 like that. And you would graph that way. So a slant asymptote is it's the quotient in your long division, synthetic division of your polynomial, and whatever that quotient is ends up being the equation of it. And then you draw that equation using slope-intercept form. A lot of the rest of that I kind of answered. I talked about even oblique asymptotes such as a quadratic and stuff. Not how to graph a quadratic, but the fact that you can have a quadratic one, which is kind of interesting. Okay, let's go to this. Can you go over sign charts again? Here, I'll say that I answered it on this one. What's the best way to determine where the lines go on a graph? So I'll do just one little bit as far as the physical nature of them. But I don't think I'm going to do a full problem again, just as whatever example that I made up at the time. So sign charts. Let me just talk about the benefits so I'm not answering the whole thing again. Well, I'll end up accidentally going over the whole thing again. I don't really want to. But when we're graphing these things, we're only trying to come up with critical points. I'm not getting, whenever I draw a curve, like saying, oh, it's approaching this and it's approaching that, I probably missed where this thing actually hits. It probably hits right here and right here and right here and right there, and I probably missed the actual points that it hits. But I'm trying to get the general behavior. We're approaching this asymptote right here and this asymptote right there, and I just want to know that. Right? So understand that we're not necessarily getting the actual y values at those x, but we are getting the actual gist of it, meaning the idea of it approaching, staying positive, and curving, and all those kinds of things. That's the general thing we're trying to get. Therefore, I'm not plugging in actual x values and getting actual y values out. I'm not doing actual computing. But I do need to know if the points are above or below an asymptote, to the left or to the right of a certain asymptote. Right? So here's what a sign chart's all about. Again, I'm just going to kind of make up some things. I'm going to draw a bunch of vertical asymptotes right here. Draw a bunch of vertical asymptotes right there. I'm going to draw myself a horizontal asymptote, and I'll do it again at y equals 0 right there. The idea of a sign chart comes into play when you really, really need to find out the signs of some values, and that'll be because you didn't find any other points, something I already talked about before. But let's say that we also had some other points here, and I really am kind of going over the stuff again. Let's say I know it crosses the x-axis there, and I know it crosses the x-axis here as well, because I found x-intercepts, right? A sign chart, I don't know whether the points what the points did to go through here. I don't know whether it went through this way, or whether it went through this way, or whether it bounced off, or whether it bounced off right there, right? I don't know whether the points are below or above the asymptote here. I don't know whether I approach below or above or below here. I don't know whether this thing crossed through on the top, crossed through on the bottom, things like that. This is where a sign chart's used. You'll notice the values change signs potentially. They change sign values of y when we hit, instead of an x-intercept here, I'm going to put a hole just to be even more fun with it, just to make sure that you understand. As long as it's crossing an asymptote, or it's going on the other side of an asymptote, and you're well aware of those values where they do cross or go on the other side of asymptotes, signs can potentially change, right? This can go from positive to negative to positive to negative to positive to negative, just like that, right? You could find all those things right there. This could very well be our graph. I have no idea. I don't even have an equation for this. I just made this thing up. But this could very well have done all those things, and all those signs could have changed in that way. Or they might not have changed at all. Maybe instead of this thing being negative down here, maybe it's positive on the other side, just like this. I don't know if we've run into a graph like that together yet, but it totally can do that, right? Even function kind of behavior. But this can totally be the graph. A sign chart, you don't need the chart specifically, but the chart would kind of be like a number line, and then you could say to the left and right of some of these values, and I don't know if my sign chart's any better visual than any other ones, but here's x equals -8 is right there, where it could potentially to the left of it be positive and to the right of it be negative. So let's say we just follow that sign chart. You plug in a value to the left of -8, like -10, in your equation, and you get a positive value out. That means that to the left of -8, everything's going to be positive, because there's no other critical value. Because here's the idea. If you know that you don't have any other points where it crosses the x-axis, and you don't have any other vertical asymptote, there's no way this thing can cross the x-axis again. There's no way it can go on the other side and become negative. It'll stay positive the entire time. There's no way that it can't. There's no way that it can. Tell me how I can go from negative to positive up here without crossing the x-axis, without jumping a hole, or without having a vertical asymptote right there. You can't. You can't. So what happens between -8 and -5? Well, apparently to this made-up equation, it's negative right there. Everything down below is negative, and it's going to stay negative. So you got to plug in a value like -7 or -6. And when I say plug it in, I mean come up with what the signs are. When I'm talking about sign charts, I don't care what the value is. You can compute it. You can do whatever you want. You plug in -7, let's say you get -1.5. Great. You got a value. I just care that it's negative. And I just know that the rest of it's negative from there. That's the only thing I care about right there. This between -5 and 0, what's going on right there? Apparently they were positive, right? You plug in -2. and you get a positive value out. And because I know it doesn't cross the x-axis at all, because I know they're two vertical asymptotes, it's got to approach them. It's going to stay positive the entire time. You plug in -2, you get positive. You plug in -1, you're going to get positive. I don't care what the values are. I know they're going to approach because I know the nature and behavior of these rational functions based on what I drew so far. And then there's another critical point right here between 0 and 3. I already said I was going to answer this. Now I'm answering it. Between 0 and 3, apparently it was all negative. And the idea is, remember, this thing could go through after that. It could bounce off and go negative, and I'm not sure which one. But to the left of that x-intercept, where it at least touches the x-axis, the asymptote right there, it was negative. And then to the right of 3, apparently it was positive here, but between 3 and, I guess, 6 I made up right there. Between 3 and 6 it was positive, and it very well could have been negative. It could have bounced off. I don't know. I don't know how to make an equation that does that. But it's positive right there. You have to plug in something like 4 or 5 or 4.5. Plug in something where you can know in factored form whether you get positive or negative. This is positive. And to the right of 6, as I made this thing up, it's also positive right there. It stays above because it can't cross in any sort of way. So what a sign chart is doing for me is I'm substituting, again, I did this with an actual equation in numbers before. I'm plugging in a value that's to the left or right of a critical point where it crosses an asymptote or where you're to the left or right of a vertical asymptote. And this asymptote doesn't have to be on the x-axis. It could be above or below. That's another mention I made. It could be above or below the x-axis. It could be slanted. And that's where I would try them in the remainder because the remainder just determines whether you're above or below your quotient, your actual asymptote itself. And that's where we would do those ones there. So you plug them in. I would do it in factored form to not care about the signs or the values, but just care about the signs. And a positive times a negative is negative. Positive divided by negative is negative. Negative divided by negative is positive. And positive times positive is positive. You can come up with them pretty easily there. And if you see some of my examples that I do, that's where I work them. But I don't need a sign chart if I know where certain points are already. In this case, I needed to know because I didn't have a y-intercept. But hey, if the vertical asymptote's here, then I probably get a y-intercept right there, and then I know it's positive. I don't have to do more work. Or if my x-axis is right there, or the asymptote's right there, then I know it crosses the x-axis right there because I get x-intercepts, you know? So I don't need a sign chart all the time. I only need them when I don't know where points exist to the left and right of critical x values, asymptotes, holes, and intercepts, or where they cross the asymptotes. Okay, last question. Can you explain a little bit more about the graphing the points part? I kind of just answered just right at the very end there, but the whole idea, the order in which we go, this is the last question I'll just answer here. Or it is the last question. Only 6 of them. And I did actually spend a power hour on this. The order in which I generally do our things, and maybe I can do a full example with you guys. Let me find one online. Give me 1 second. Let's search together. I'll go past the hour. Let's type in graph rational functions example. Okay. And I don't want to see the graph itself before I get the answer. I just want to come. Well, I don't mind seeing the answer just to go like, all right, it's going to be that kind of answer. Sorry about this. I should really pause here. Let me pause the video and actually get an example. Give me 1 second. All right, on this page, I found a treasure trove of them. And I don't know. I'm just going to look at some of the answers, see what's going on. Okay, so that one's pretty fun. So let's do this one right here. So 2x squared, let me write this down and then I'll get to us and just talk about the order of the points. Because I don't know what you're asking specifically when it says the points again. I'm sure I answered some of the other things. But let's talk about what features we can find. 2x squared minus 2x minus 4 divided by x squared minus x minus 12. Okay, so let's go back to this. And, you know, I'll rummage through this in terms of talking about the things we got to find. Okay. In finding points, remember, you can always plug values into a table, but have fun with that, right? If I plug, hey, let's plug in 1 for x. All right, 2 times 1 squared minus 2 times 1 minus 4 divided by 1 squared minus 1 minus 12. It's probably some weird fraction. You know, it doesn't work, right? Let's plug in 6 for x. All right, 2 times 6 squared. Have fun with a table, guys. Even if you had a table thing on your calculator and came up here. Dude, here, before we... hey, dude. Before we even get into that, here, let's do... Let's come up with one. I mean, you know how these are graphed now, so it's not as fun this way anymore. But okay, let's do Sorry, I'm going to go past the hour easily. I'm trying to find how to get on here. Okay, I came up with 1 over x minus 1. Even if you wanted to plug in values there, I think that's a little too simple. But okay, let's plug in 1 for x. Oh, it's undefined. That doesn't work. You might not even know what that means at that time when your calculator's like, what did that give you? And 2 for x, 3 for x, 4 for x, 5 for x. You get all these numbers right here. Have fun plotting them, and then you end up getting those points right there. And then what? What does that graph look like then? You plugged in some values, and then you plug in 0 for x as well. Let's go back down there. Plug in 0 for x, and then your point's right there, and you plug in -1 for x, and you're like, what is happening? You know what's happening, right? So plugging in values doesn't work. You know what the graph looks like? Like that, right? So it's something where if we can come up with the general nature of the graph, we understand where asymptotes are and stuff, that'll be helpful. So the general gist of what I'm talking about right now to start with is I need to find out where the asymptotes are. I think approaching the values would be, I know approaching the values will be the best way that any teacher will tell you. Anybody, any website and stuff is going to tell you all about asymptotes and features and things like that. This isn't a me thing, and I hope you're understanding of that. But it being a me thing, one way or the other, means I'm going to give it as most efficiently as possible. So here's what we want to do. We want to factor this thing first. Factoring gives us a lot of information, and it helps us out get more information from it. I got a GCF of 2 up top, and on bottom I can factor x minus 4 times x plus 3. And then also on top, this can factor into x minus 2 times x plus 1. Okay, what does factoring give us? It tells us there are no holes. There are no holes because, and that's the first thing I kind of look for after factoring. Holes, none. There are no holes because I never divide 0 by 0. I never have a common factor on, if this was x minus 2 over x minus 2, then x couldn't equal 2 because you'd get 0 over 0 from that. You could also cancel those out though, because the idea is the simplified equation can say what the graph looks like without that part present, as long as we acknowledge where the hole is. But given that, and sorry that I don't have a whole example, but if this was x minus 2 over x minus 2, then I could plug 2 for x into here, 2 times 3 over 5, 6 over 5, and figure out where the location of that hole is to graph one of those points. But there are no holes here, so no feature yet. However, there are vertical asymptotes. There's a vertical asymptote at x equals 4 and x equals -3, and this is huge information for us when it comes to us graphing. Right? This is information that says, all right, well, I know that there's going to be a line right there and right there that we get to approach, either to positive or negative infinity, and all that. As far as horizontal asymptote goes, I've already kind of mentioned before, it's at y equals 2. There's a tie. There's a tie right here in these x's right there, x squareds, and you're dividing 2 by 1 as a result of that. So there's one at y equals 2 right there, which means we're either above or below and such. We could figure out if this crosses the asymptote in some certain situations by doing like a long division. We could do something like that. Let's just figure out what kind of points we do know. Let's find the x and y intercepts. X intercepts. We set y equal to 0, and we find out when the numerator is 0. That's something that I answered earlier. So there's an x-intercept at 2, x equals 2, and x equals -1. X equals 2 right there, x equals -1 right there. It actually crosses the x-axis twice there, and it doesn't do it again. It crosses the x-axis here and here, and it doesn't do it again. There's a y-intercept as well. A y-intercept, when you plug in 0 for x, I'll do it in the top, you get -4 divided by -12. That's at positive 1/3, which is right there. So positive 1/3 like that. Now, based on the nature of this quadratic thing, something I think this graph is telling me right now, and it's, again, based on kind of the location of the points, is I don't think the graph is going to go through here and curve itself back up like that. It's more likely the graph is going to stay below and do that. Given what I have so far, I am likely determining the outcome of the graph to be something like this. And honestly, I forget what the answer looks like in the other thing. I do not remember. And probably something like this right here. And the main reason why I'm saying that is because these are the only two x-intercepts. We know there are no x-intercepts here, so we know it doesn't cross the x-axis here, which means it cannot approach from down below there. Otherwise, we'd have an x-intercept. And it cannot approach from down below there because it doesn't have an x-intercept. The only other question that I have involved now is, does it cross the asymptote at any place? Because it's possible. The graph, instead of just starting above and doing that, is it could cross from above, hit the asymptote, and start and go underneath right there. And the times that I want to check this are when I have two vertical asymptotes or more, and a horizontal asymptote not on the x-axis, because otherwise I'd know where the x-intercepts are. If it were on the x-axis, then I know it would cross. or if I have a slant asymptote, because I got to do long division anyway. So I'm going to use long division on the rest of this thing and see where this graph potentially goes. So let's undo those. Let's figure out where it crosses the asymptote, if at all. And if it doesn't, great. Whoops, let's leave those features. So here I'm going to use long division. I can't use synthetic because I got a quadratic unless I do it twice, and I'm not going to. X squared minus x minus 12 there, and 2x squared minus 2x minus 4 right here. I'm just going to do it once. X squared goes into 2x squared 2 times, and then you multiply that out. You get 2x squared minus 2x minus 24, and that becomes 20. So this becomes f of x equals 2 plus 20 over x squared minus x minus 12. Okay, this answers everything else I need to know. Obviously, horizontal asymptote at y equals 2. We have that. Plus 20 over this. Our question becomes, can the remainder ever turn into 0? Can I ever plug in an x value in the numerator right here where I see a 20 and get 0 out so the remainder becomes 0? If the remainder could become 0, that means I could find the x values of that where it would cross the asymptote. Let's say I plugged in -7 for x, and that would give me 0 on the remainder. That would mean I'd have y equals 2. Because 20 is the value, there's no way that I can plug x into 20 and get 0. Just saying 20 equals 0 doesn't make any sense. So there is no place where it crosses the asymptote there. That means I'm done with my features. I know it never crosses the asymptote. I know it crosses at these specific places here, and it's got to hit those points on the curve. And I don't have to use a sign chart at all in any sort of way because I know what it does and does not hit. It stays above here, never crosses. It stays above here, never crosses. That is going to be my graph. So I don't know, that was just one example. I didn't know how to answer that without saying, I wanted to talk about features and where you get those features from. This is just one example. There's so many examples you can do. Obviously slants, obviously crossing asymptote, obviously holes, things like that. This was just one example. I wanted to do that. All the rest I have covered in the other things. So let's see what that answer actually did look like going back right here. This is where I'm going to wrap this thing up. I think it was this one here. Answer. And we got the same thing here. Looks like they decided to plug in some points for you guys. They plugged in like 6 or whatever that is. Not 6. What is that? 2, 4, 5. They plugged in 5. They got a value. They plugged in -1, 2, 3, 4. They plugged in -4 and they got a value there. I don't need to plug in those values because I know, based on the points that I found, including the y-intercept there and not crossing the asymptotes, where it's going to be above and below. So they decided to get a few more points like that. I didn't need to. If you want to, great, you can use a sign chart that way, but I would use it on the long division aspect because you're not trying to find out whether your points are positive or negative. This is where I'm going to stop talking after this. You're not trying to find out whether your points are positive or negative. You're trying to find out whether they're above or below the asymptote. Right? If I plug in a value, if I plug in -5 into this thing, into the factored form, which I got rid of, if I plugged in -5 and I found out the value was positive, how do you know that it's not positive right here? That's a positive. Positive 1's a positive number. How do I know that it's not that graph and it's not positive right there? I want to know whether the remainder is positive. I want to know when plugging in -5 whether I'm above or below the asymptote. If the remainder is positive, then I'm above 2 plus something. If my remainder is negative, then I'm below it, 2 minus something, right? But I don't need to do that here because I knew it didn't cross. I found all the features I needed. I know it doesn't cross the x-axis either, and I'm good. All right, guys, that is past the hour and power hour here. It's a true definition of power hour plus, and I sure hope you enjoyed that. So that'll be it, guys. This is Mr. Robinson. Thank you so much for watching. And if you lived through all this stuff to watch it, I hope you really absorbed what's going on. Get some practice on it. I will see you in the next one.